There are 6 basic flight instruments which are designed to provide you with the information you will need to control the airplane. Let's begin by looking at the pitot-static instruments. The pitot-static instruments include the airspeed indicator, altimeter, and vertical speed indicator. Because these instruments operate on the principle of pressure differential, you need to understand how the atmospheric pressure surrounding your airplane changes in various situations. For example, as you climb to a higher altitude, the density of air decreases. Therefore, the pressure of the air is lower. The pitot-static instruments are able to sense the changes in atmospheric pressure and provide you with information concerning your airspeed, altitude, and rate of altitude change. During flight, the pressure surrounding the airplane enters the instruments through a static port, which is positioned in an area of relatively undisturbed air, such as the side of the fuselage. At the same time, ram air pressure enters through a small hole at the front of a pitot tube, which is mounted so it is exposed to the relative wind. While all 3 instruments use the ambient air pressure provided by the static port, only the airspeed indicator uses ram air pressure from the pitot tube. The airspeed indicator displays the speed of your airplane through the air by measuring the difference between the ram air pressure entering the pitot tube and the ambient air pressure that enters the static port. As this pressure differential changes, the airspeed needle moves. A number of color-coded arcs are incorporated on the instrument face and represent various airspeed limitations. For example, the white arc shows the flap operating range. The upper end of the white arc indicates the maximum airspeed permissible with flaps fully extended, while the lower end shows the stall speed with full flaps. The white arc becomes very useful during the landing phase of your flight because it helps you determine when you can safely extend the flaps. It also shows you when you're approaching the normal stall speed in the landing configuration. Most of your flying, however, will occur at airspeeds within the green arc, which is known as the normal operating range. The lower boundary of this arc shows the airplane's stall speed when it's at the maximum takeoff weight with the flaps up, and, if applicable, the landing gear retracted. The upper limit of the green arc is the maximum structural cruising speed. You can exceed this airspeed and begin flying in the yellow range only when the air is smooth and only with caution. Finally, a red marking is placed at the never exceed speed. You should never operate above this speed because structural damage could occur. During your flying, you will become familiar with several types of speed. For example, indicated airspeed is read directly from the instrument. However, when calculating airplane performance, you should use calibrated airspeed, which is indicated airspeed corrected for instrument and installation errors. You can determine calibrated airspeed by referring to the table provided in the pilot's operating handbook. True airspeed is your actual speed through the air. It is calibrated airspeed corrected for density changes due to altitude and non-standard temperatures. Another term, ground speed, describes your actual speed over the surface. In a no-wind situation, true airspeed, or TAS, and ground speed, GS, are equal. A headwind, however, will decrease your ground speed. Conversely, a tailwind will increase it. Now let's look at how the altimeter works to provide you with altitude information. The altimeter senses pressure changes in the surrounding atmosphere and converts this information to a display of your altitude. Most altimeters have 3 pointers. The longest shows hundreds of feet, the middle-sized pointer, thousands of feet, and the shortest one shows tens of thousands of feet. To properly read an altimeter, you must first look at the shortest pointer. In this case, it's between 0 and 1. Indicating you're below 10,000 feet. The middle pointer shows that you're somewhere between 5,000 and 6,000 feet. And the longest pointer shows you're halfway between 700 and 800 feet. Putting the three together, you come up with an altitude of 5,750 feet. Be very careful when reading an altimeter because misreading it could lead to serious consequences. The altimeter also has a barometric scale which can be adjusted to compensate for variations in atmospheric pressure. Here you can see the numbers 29.9 and 30.0. You read these by adding a 0 to each number to get 29.90 and 30.00 inches of mercury. The barometric setting on this altimeter is read as 29.95 since the pointer is halfway between 29.9 and 30.0. As you can see, the distance between the printed numbers represents 1/10 of an inch of mercury. Since the barometric pressure changes approximately 1/10 of an inch for every 100-foot change in altitude, moving the scale 1/10 of an inch will cause the pointers to move 100 feet. Altimeter settings are provided by FAA facilities such as control towers and flight service stations. Before every flight, you should adjust the altimeter to the current reported setting. If you set it correctly, your altimeter should read the field elevation. Then during your flight, especially if you're leaving the local area, you should periodically adjust the altimeter to the latest reported setting. Let's see what might happen if you fail to make these adjustments. Suppose you're maintaining an altitude of 5,500 feet and you're flying into an area of lower pressure. The altimeter interprets the decreasing pressure entering the static port as a climb, although you're actually flying level. When you notice the altitude gain, you will naturally lower the nose to descend to your desired altitude. However, in this situation, you will actually be descending to a lower altitude, even though the altimeter shows a return to 5,500 feet. To a certain degree, this same situation occurs when you're flying from an area of warmer air to one with cooler air. Obviously, this could be dangerous if you're flying over obstacles or high-rising terrain. It could also place you far off your appropriate VFR cruising altitude. A helpful memory aid to assist you in determining whether you're higher or lower than before is the phrase, "When flying from high to low or hot to cold, look out below." This means that in these situations, you're going to be below the altitude indicated on your altimeter. The best way to minimize this type of error is to periodically reset your altimeter to the current setting as reported by the nearest FAA facility. Keep in mind that an altimeter measures altitude above a specific reference. There are various types of altitudes depending on which reference you are using. For example, indicated altitude is read directly from the instrument. If the proper barometric pressure is set in the altimeter, its indication will be based on a standard plane called mean sea level, or MSL. In other words, if your altimeter is reading 2,000 feet MSL, you are actually flying 2,000 feet above this standard sea level reference. The distance between your airplane and sea level is called true altitude. If you're flying over a surface higher than mean sea level, you must subtract its height from the altimeter reading to obtain your distance above the surface. This difference is called absolute altitude and is often referred to as height above ground level, or AGL. Pressure altitude is referenced to a standard level of 29.92 inches of mercury. It is used with the existing temperature to determine density altitude. Density altitude is pressure altitude corrected for non-standard temperature. It is not really an altitude, but is a theoretical value used in the computation of aircraft performance. Now let's take a look at the last pitot-static instrument, the vertical speed indicator. Like the altimeter, it is connected only to the static port. As you climb or descend, the VSI measures how fast the ambient pressure is changing and displays the rate of altitude change in feet per minute. In this situation, you're descending at 300 feet per minute. One of the most valuable uses of the VSI is that it immediately provides you with trend information when you begin to gain or lose altitude. After a few seconds, the VSI stabilizes and displays the actual rate of altitude change. Although the pitot-static instruments provide you with essential flight information, you need to use them in conjunction with the other instruments to precisely control your airplane. Gyroscopic instruments give you information about your airplane's attitude, its rate of turn, and its heading. These instruments include the attitude indicator, the turn coordinator, and the heading indicator. Before we take a look at the information these instruments provide, you need to understand how they operate. The primary element of each gyroscopic instrument is a heavily constructed spinning gyro mounted in gimbals. If the gyro is freely or universally mounted, it will remain in a fixed position no matter where you move its base. This degree of stability is known as rigidity in space. If the gyro is mounted in an instrument so the airplane can rotate about it, the aircraft's movements will be displayed on the instrument face. Most small airplanes use two different sources of power to spin the gyros. Typically, the turn coordinator uses electrical power, while the attitude indicator and heading indicator are driven by a vacuum system. By using two independent sources of power, you will still have some degree of backup should one system fail. A vacuum or suction gauge is normally positioned on the instrument panel to allow you to monitor the vacuum pressure. If the pressure is not at an adequate level, the gyro instruments could be unreliable. Now let's take a closer look at the attitude indicator. This instrument senses rolling and pitching movements, providing you with a pictorial view of your airplane's attitude in relation to the natural horizon. The attitude indicator uses a miniature airplane and an artificial horizon to show both angle of bank and pitch. The artificial horizon is controlled by the spinning gyro. Index markings are incorporated to show you precisely how much pitch and bank you're using. An adjustment knob enables you to align the miniature airplane with the horizon bar before takeoff and during straight and level flight. As you enter a level left turn from straight and level flight, the attitude indicator will detect and display the change in bank. In this situation, you are maintaining 30 degrees of bank. As you roll back to wings level, the attitude indicator will give you the same indication as the actual horizon. When you enter a descent from straight and level by lowering the nose, the instrument again displays your position in relation to the actual horizon. A combination of pitch and bank is shown just as easily. For example, during a climbing right turn, the nose is above the horizon, and the miniature airplane is banked to the right. Now let's take a close look at the information displayed by the electrically driven turn coordinator. The turn coordinator is actually two separate instruments. One instrument contains a spinning gyro which senses rolling and yawing movement. A miniature airplane on the face of the instrument represents the actual airplane and indicates your turn rate. For example, as you roll into a right turn, the miniature airplane will bank in the same direction, showing you how fast you rolled into the turn. Once the turn is established, it indicates how fast you're making the turn. It does not, however, show your actual bank angle. During certain maneuvers, you will be required to perform a standard rate turn, which is a turn rate of 3 degrees per second. This means that you'll be turning 180 degrees in 1 minute, or making a complete 360-degree turn in 2 minutes. When the miniature airplane's wing is aligned with the lower index mark, you're in a standard rate turn. The second part of the turn coordinator is the inclinometer, commonly referred to as the ball. It consists of a curved glass tube containing a ball that moves in response to gravity and turning forces. The ball is used to establish and maintain coordinated flight. For example, during straight and level coordinated flight, the force of gravity causes the ball to settle in the lowest part of the tube. During a coordinated turn, the ball will still remain centered between the reference lines. However, if the bank becomes too steep for the turn rate, the ball will move to the inside of the turn and indicate a slip. If the bank is too shallow for the turn rate, the ball will move to the outside of the turn, indicating the airplane is in a skid. You can center the ball by varying your angle of bank, or by applying rudder pressure in the direction of the deflected ball. To help you determine which rudder pedal to press, use the saying, "Step on the ball." In other words, if the ball is out to the right, step on the right rudder pedal. The final gyroscopic instrument is the heading indicator, sometimes referred to as the directional gyro. Like the attitude indicator, it receives its power from the vacuum system. The heading indicator is a relatively simple instrument to read. The graduations on the face are spaced at 5-degree intervals, with the cardinal headings north, east, south, and west marked with a letter. Between the cardinal headings, each 30-degree increment is marked by a number with the last zero omitted. This instrument is showing a northwesterly heading of 330 degrees. Because the heading indicator does not have a magnetic north-seeking element, you will have to set it prior to each flight. You will also need to reset it during flight to counteract gyroscopic precession. The instrument to use when resetting the heading indicator is the magnetic compass. Since it is not a gyroscopic instrument, it will not experience the same errors which occur in a heading indicator. In addition, because it doesn't require any power, it is an important backup source for heading information. However, a magnetic compass does have its own limitations which you should be familiar with when using it for directional information. For example, when a compass is mounted in an airplane, metals and electrical equipment produce local magnetic disturbances, resulting in a slight error in the indication. This error is called deviation. A correction card is mounted near the compass so you can correct for any deviation. For example, in this airplane, if you want to fly a magnetic heading of 090, you'll need to fly a compass heading of 088 degrees. The compass is also affected by magnetic dip, which is the tendency of a compass to point down and toward the magnetic poles. This error is greatest when you're near the poles. As a result of magnetic dip, your compass will give an incorrect reading when you turn, accelerate, or decelerate. In the northern hemisphere, a turn from a northerly heading results in the compass initially indicating a turn in the opposite direction, then lagging behind the actual heading. This lag decreases as you approach an easterly or westerly heading. In a turn from south, the compass will indicate the proper turn, but will lead the actual heading. As in a turn from north, this error diminishes as the turn approaches east or west. Errors also occur when you're accelerating or decelerating, especially if you're flying on an east or west heading. When you accelerate, the compass will indicate a turn to the north, even though you're still flying straight and level. The opposite is true when decelerating. In this case, the indication will be toward the south. A simple memory aid to help you remember which way the compass will move is ANDS, which stands for accelerate north, decelerate south. When you use the magnetic compass to reset the heading indicator, remember these limitations and reset it only when you're flying in straight and level, unaccelerated flight. Once you've achieved the ability to use and interpret the flight instruments correctly, you should be able to control your airplane with more precision. This will make your flying easier and make you a more proficient pilot.